Did you send out the Zoom link like you said you were going to?
No, what I'll do is I'll post it on the homepage and I'll create one from Zoom and then we'll just keep using that same one over and over again. Zoom's weird, it sets up meeting times and then it doesn't care. You can start a meeting anytime. Um, and then for the video, assuming the sound quality is acceptable, I'll post those. I think I'm going to post those to YouTube actually, so I'll have those links. And I'm looking at what I had last summer, and I basically had a link for each class. So this hasn't changed radically. I didn't change this at all, but I mean the text of it. But S1 is on Monday. Other than that, so far we're good. Schedules tend to be flexible because you never know what's going to happen, especially in the fall semesters. Okay, so let's make sure. All I'm going to do is say, here's some definitions, and talk about how they fit into the larger scheme of things. We've already talked about what a model is. It's a representation of a real world thing. Then we've talked about what a simulation is, which is a exercise of that model through some kind of interaction with an environment or with other models. We talked about what an agent is, which is a decision maker. And so we get interesting results when we have multiple agents interacting together in a system. People study, we're going to do everything in the simulated world. People do study more and more interactions between humans and non-human agents. So the human is just treated as another agent in the system at that point. The reason that people are doing that is because, as you know, we're having more and more sophisticated agents in our life. The idea of working with a robot in terms of the way you work with a human has not been fully realized yet, maybe in some minor applications that I don't know about. But if you hear about, and I'm not up to speed as much as I maybe could be on this. You hear about like warehouses that are being restocked, or you have an order to go get some parts and the human doesn't go run around the warehouse and get the parts. The robotic entity runs around the warehouse and gets the parts. And I'm saying run around, but they're typically wheeled vehicles and they're able to pull things out of bins and things like that. And then they can do the restocking the same way. And then they should be smart enough to go plug themselves in when they need to recharge. Well, ultimately that robotic agent has to interact with a human. And so the question is, how much does this interaction work out? What can you do? And then you can start to make more sophisticated scenarios. So, let's say you want to move a couch, or you work for a moving company, and instead of having 3 people in the truck, you've got one person and a robot, so now you need to move the couch. You've moved a couch with somebody before, probably, or moved some heavy furniture with somebody before, probably. And I did this a lot with my son, and it took me a while to train him so that he and I could work together as a team, right? So he knew what I was expecting and how we were going to turn the furniture to make corners and things like that. Well, now think about doing that with a robot. The stuff you take for granted with a human, by the way, you will be shocked to find that the robot probably isn't aware of or capable of doing, right? We do a lot of things through social norms that act as shortcuts. And so far, robotic entities or software agents haven't really adapted to that. So that's actually a topic of study. How could you introduce social norms or have robotic entities that learn social norms? And that's what we talked about, the opera problem yesterday, getting all the robots out of a room. Basically, what they're doing is learning or creating social norms that help them cooperate and share that resource. Dr. Sean Dougherty in Human Factors Department. Anybody know him? If you need to get an elective, take a class with him. He's really good, right? So he is interested in building like virtual escape rooms. And so in a virtual escape room, you could have several humans, just like an online game, participating in the same virtual space. But if I'm a human participating in the virtual space with another human, how do I know you're a real human and not an agent? In other words, I could replace that human with a software agent, right? And now I'm cooperating with an agent. So that's an opportunity for research. And if somebody wants to build a multi-user escape game where you have a software agent and a human working together to get out of the escape room, that's not a bad project. And the reason it's not a bad project, even though it's a game, is it actually can be used as a research tool. Especially if you have to make it where you can dial up and down the autonomy of the agent, right? So
that, and also make it where the person is able to tell it's a robot by the label of it and not.
exactly. And people actually, I was part of an experiment years ago where people were taking by the way, psychologists always lie to you. Okay, so if you're going to be an experiment with the psych people, they're always lying to you. Okay, so we had set up a maze, and then we had a robot car, and then the robot car would go through the maze, and the human could give basic commands to the car, like turn left, turn right, you know, that kind of stuff. What they didn't know, the humans that were giving the commands, was that the car had no autonomy whatsoever. It was a radio controlled car. And the human that was controlling the car would make the car perform badly to see how the human who was ostensibly its partner would react. And so then what they did is they dressed the car up in just, here's like a, you know, an F-250 black pickup truck. Or then they put a skin on it that made it look like an ugly mask. And then they put a skin on it like a fuzzy little bunny. And what they were really measuring was how do people interact with the robot agents based on its appearance. And of course, when it's the fuzzy little bunny, they're like, a lot of people were like, okay, that's a wrong turn, but that's okay. You're still a good little robot, you know? And when it was just a car, it's like, God, you're such a stupid shit, you know? So the real experiment was, how do you generate the kind of interaction with the kind of empathy that we tend to show towards other rational agents or humans? And so that was just kind of an interesting experiment. They did some more with how much of a face does something need to have before people start to anthropomorphize it. So you can just have just basically, and you've seen this, Volkswagen Bug from head on, and it's kind of got a face, right? Or a lot of cars do. And so people, we can't help it, we're hardwired. We automatically work with that stuff. Okay, so anyway, those are kinds of things that you can think about. It may be that it's too sophisticated a project to pull off in the summer to get a real live escape room, but you could develop some simple abstract tasks with a robotic agent or a software agent, and then you can play around with, again, dialing up and down both the autonomy and the competency of the software agent. Yeah.
It'd be funny if you could make it where the other person, you have two people, but they both think the other person's a robot.
Yeah, you can play those kinds of games. And if you build the system right, where it's modular, you could plug out the software agent and put a human in. And again, that would be a standard psych trick, is to tell someone they're dealing with a software agent, but really it's a Wizard of Oz human directing the software agent and either having it do well or do poorly. And then in terms of screening, you could just have a simple icon that's a cute little fuzzy face or a more grotesque face or something like that. So you can create these things fairly easily. And then if you do and we like it, go tell Dr. Dougherty and see if he wants to use it, and go through the whole IRB process and all that. Okay. But back to basics with simulation. We talked about computational fluid. I'm not sure what we've all gone through. Oh, okay. So discrete event simulation is where we ended up yesterday, where you are not dealing with continuous time. You set things up as a schedule. Okay, the next event happens here, the next event happens here, the next event happens here in terms of time, and your simulation just jumps to the next event, jumps to the next event, jumps to the next event. That can be computationally efficient, particularly if you have events that either don't occur very often, so you're rather sparse in terms of events over time, or a lot of, like I said yesterday, a lot of queuing models will use that where they're like, okay, the next customer won't come into the shop for another 10 minutes. So I'm not going to waste my computation cycles, you know, going through every second of the next 10 minutes. I'm just going to jump. Because basically what's going to happen is you're going to have a state change within the overall simulation at that point. So you're jumping from state change to state change to state change. Numerical methods are closely related to simulation. If you talk to the math people, right? You can get a degree in this university in computational mathematics. And in fact, who's CS? Your CS and your CS. Standard track or cyber?
Standard.
Standard?
Cyber.
Cyber. Okay. With standard, we deliberately put in a boatload of electives. Have you noticed that?
Yeah.
So you need to get a minor. That's the goal. Get a minor. I've had 2 people graduate with dual degrees, computer science and computational mathematics, and they didn't have to take any extra classes because we put so many electives in the CS program, and so many of the courses double up for the 2 programs that you can use all your electives for the computational math required courses and get a double major when you leave here. So just bear in mind. Okay. They use numerical methods, which tend to be you've heard about this in your calc classes like Newton's method or L'Hopital's rule, things like that, right? Where you can do integration by parts, right? How do computers do integration? They don't necessarily actually do the integration the way you do. They really do the trapezoid slicing, and you have smaller and smaller delta x's, and you get a good estimate of what the result is. Yeah. I know there are some piece systems out there that will actually try to do the integration. Okay, the way we do it. It's different. All right, so the idea here is there are systems by which you can do these iterations over time or through small changes in a variable, and there's a number of techniques that exist out there, right? So that's what those things are. Agent-based simulation we've talked about already. An agent is a decision maker. Agent-based simulation is one in which multiple agents are interacting with each other, which is really the focus, should be the focus of the simulation. The trick, of course, is to get agents that behave in a meaningful way. You really want to have a valid model. A valid model means you can take the results and apply it to the real world. Then you need to have agents that are acting in a way that will produce valid results. So when you're doing a traffic model, not every driver on your simulated road is going to be, you know, driving on the shoulder and crashing into everybody. That's not valid. Okay, then different uses. Training simulations. The idea of a training simulation, as you would guess, is to provide some kind of training. The military has spent, I don't know how many good billions of dollars creating training systems. This has happened since the dawn of time.
First one in 2006, we had a combat simulator that essentially was a militaries. Games are better than
well, and is it Call of Duty that was like an outgrowth of there's some interaction between the DoD simulations and the gaming market, right? So the idea, yeah, and depending on where you are, right, depending on what your role is, the ability to have good simulations changes radically. So, for example, pilots have had pretty good simulators for decades now. Why? Think about why. Because you're in an enclosed space, right? When you're in a pilot in an aircraft or a navigator in an aircraft, you're in an enclosed space, and your interaction with the external environment basically is non-existent. Your entire interaction is with the vehicle.
And you're in the air.
And you're in the air, so you don't have to worry about terrain. So hopefully, if you have to worry about terrain, you're doing it wrong. So, well, actually, pilots, helicopter pilots worry about terrain because they fly map of the earth type stuff. Yeah. So anyway, that's been done for a long time. Infantry, though, you're intimately connected to the ground. You're moving things. You're blowing holes in walls so you can enter buildings. You know, you're digging trenches to protect yourself. Whatever. That kind of interaction has not been simulated yet. So it's more normal to take for infantry exercises to actually go out and physically go out into the real world. And we have a name for that too. That's a simulation also, constructive simulation. In Fort Benning, Georgia, if it's still called that, and other places, they have something called mounts. What's the M? Something urban terrain. MO urban terrain. And it's basically a pretend little city. It's a pretend little village. And they go out and continuously invade this village over and over and over again. So the idea is you can't do a virtual simulation of that, but I can build a pretend town. It's not a real town, it's a simulation. Doesn't have a mayor, right? It's a simulation. And then you can pretend defending it, you can practice defending it, you can practice invading it, right? That kind of thing. So they run these exercises on these real physical terrains. That's a training simulation. It's still a simulation. You may have seen movies where the army is doing these war games, right? They have red force, blue force, and they have referees, and you go out. It's like playing paintball, but you know, with real stuff. Those are simulations, training simulations. The goal is to get you to learn. What else can we think of? I don't know. When I was a young lad getting my driver's license, they had like driver simulations, but they were very rare. Did any of you guys have you guys ever played in a driving simulation to actually try to learn to drive? You just got in the car and hoped you didn't kill anybody. By the way, when you were first learning to drive, where did you learn? I was in a big empty field. A parking lot. A parking lot. A parking lot. A parking lot. Was that a simulation?
No.
I mean, it's an empty parking lot. Yeah, how often are you actually going into an empty parking lot?
It's a very high fidelity simulation, right? Because for that exact reason, the environment is an artificial environment, right? You're going into a space where you don't have to actually deal with other drivers on the road, and the odds of you hurting yourself or somebody else are severely reduced. So the car is not the simulation, it's the actual car that you're driving, but the environment that you're operating in is a safer, non-real environment, right? It's not a normal activity. And so in that sense, you can call it a training simulation. You simulated the environment. It's a really good simulation though, right? Okay, yeah, so live simulation, actual physical components. So we have the notion of live and virtual. Actual physical components represent the real world. Virtual, and there's a slight difference here between virtual and constructive. So live, so example, the soldiers invading that pretend village over and over again, that's a live simulation because they're dealing with real world objects. Your car in the parking lot would be a live simulation. A virtual simulation, when we say virtual, we think it's all computer generated, but there's a distinction here between virtual and constructive. Constructive means the entire simulation occurs in the virtual world, in a mathematical world inside the computer. You have constructed the entire thing. The difference between that and a virtual is in a virtual simulation, you have a human who's interacting with the simulation. So the human is still part of the simulation, but you're dropping them into this virtual space. And that's what's happening with pilots, right? When they do pilot training, right? We do pilot training right down here. Really good high fidelity live version of the aircraft cockpit. And then we put them in an immersive, in a virtual environment in terms of the runway and the air, when they're actually up in the air. So that's a virtual simulation because we've dunked a live human into this virtual environment. As opposed to when they're actually flying the airplanes, right? That's an actual practice run, right? That would be I wouldn't even call it a live simulation. They're actually flying the airplane, right? A constructive simulation, though, is one where there's no human interaction. So you can imagine that you might create a simulation of aircraft traffic flow patterns around an airport. And it's completely, once the human sets up the parameters and hits the button that says go run the simulation, everything in there is completely constructed, right? It's nothing but a mathematical construction inside of the computer. That's what constructive means. So as you're doing your own experiments, as you're developing your own simulation project for the course, that's a really big first question to ask is, do I need to be interacting with the simulation as a human, or am I going to set up some kind of a scenario and then just say, go, and it's all hands off after that. And then whatever happens is happening in there. When we do agent-based simulations like the opera problem, getting the robots out of the room, we tend to set up that scenario and then we say, okay, go, you guys figure it out. And the human has no interaction. Now, if you wanted to, you could have, okay, what is it like as if I wanted to explore again human robotic interaction, I could set up a simulation where as a human, I'm interacting with those agents as we try to get out the door, and hopefully they won't run me over, right? And then that would become a virtual simulation because now you're immersed in the virtual space. Does this distinction make sense? Online video games, virtual simulation. HITL is human in the loop simulation. So the idea with the human in the loop simulation is that the simulation actually is operating in real time, one-to-one time. And so as a human, you're interacting with it in real time. And again, online games are exactly that. They are human in the loop simulations. The distinction between, say, a human in the loop simulation and a virtual simulation, first of all human in the loop simulations are virtual simulations. However, you could have a virtual simulation where the simulation is running at 10 times speed, right? Every minute of real time is 10 minutes in simulation time. Or every minute in simulation time is 10, it represents 10 minutes of real time. So it's operating super fast. And instead of you having to interact with this thing in real time, periodically you might make an adjustment or an alignment or put some kind of an input in, something like that. You're still doing an immersive thing, but you're not doing it in a true human in the loop simulation where human in the loop means everything is responding to you in real time. A version of human in the loop that I don't think I've included in here is they put in SITL, system in the loop, or CITL, component in the loop, right? So if I'm going to, say, build an avionics box, and my avionics box is supposed to gather data in real time and report it out, I might, when I'm developing this box, not might, I will, when I'm developing this box, create an artificial aircraft and environment for this box to interact with. And then I'm going to test it by having the simulation throw stuff at it, but it's all doing it in real time. And so in that case, it's not a human in the loop simulation, it's a component in the loop simulation, right? You can test real world objects, and you should, by having them interact with artificial stuff, with simulated stuff. That's a normal way to go. Years ago, 1984, 1985, when I was first entering industry, and we were dealing with, we were building some satellite components, and our satellite components were providing power to the rest of the satellite. So our ground support team, we needed to test this stuff before we shipped it off to NASA, developed an artificial spacecraft. And this artificial spacecraft, right, this simulated spacecraft was sending commands to our device and getting power from our device, even though it wasn't using it, it was getting power from our device. So that was an idea of a component in the loop simulation. Okay, so that's the basic definitions. Now this one's just going to boatload of definitions. Some basic definitions, and now we can start to talk about process and get into a little bit more detailed definitions. So I've got two papers, they're online, one by this Maria, one by Banks. And this is the process that they're claiming you use in developing a simulation and conducting experiments and getting results. And if you notice, they align pretty well. Why should you be? I'm not surprised at that, right? Ultimately, these people are describing the same process. They may describe it in slightly different ways or focus on different elements, but basically, what are they saying? You identify the problem, formulate the problem, and in this case, collect and process real data, formulate and develop a model, validate the model, document the model for future use. That's the part nobody ever does, right? Select appropriate experiment design, establish your experiment, perform the simulation runs, interpret the results, and recommend appropriate course of action. Okay, so let's walk through that. Identify the problem. Again, this is a real world problem. Now, in your case, you may not identify a problem per se. You might identify a research question that you're interested in, a hypothesis. The problem has nothing to do with computers, simulation, anything. The problem is just something that exists organically in the real world. So, I don't know, pick a problem. What are we going to do with all these squirrels in my yard? Some kind of problem. That exists in the real world. I have squirrels in my yard. That exists in the real world. It has nothing to do with computers or simulations or anything. The reason I'm stressing this is because when I taught CS225 for a very long time, and it was very difficult to get those students to separate, here's your software, here's the thing that you're trying to model in your software. That thing exists regardless of your software, right? Okay, so then what's this? Collect and process real system data and formulate and develop a model. Why are you collecting real system data? If you're collecting real system data, real world data, why are you even building a simulation? What's the point of that step?
How are you going to know if you're trying to do that hurricane simulation? Talk about how you're going to know how fast the winds will go.
Exactly, yeah. What you're doing is you're trying to develop your math model. And you can't do that unless you know what the real world thing looks like. So the first thing you do is you look at some kind of historical data. Now, this step in this class, right, we don't have a lot of time for that. And quite frankly, a lot of this stuff's already going to be done. So if you are wanting to do a simulation that's modeling some real world event or some real world process, by all means do so. And this part has already been done for you. Other people have already done this stuff, right? You can look this stuff up. But in the first deliverable that I'm asking you for your project, the first deliverable is just tell me what you want to do. It's basically a proposal. And assuming that we like the proposal, the next section that I want you to turn in is your background section. And that's this part here, collect and process real system data. You basically describe the real world problem in a nice, concrete way. With references, with citations, right? You're going to have to do some research, almost certainly. Then you formulate and develop your model. And again, the model is the abstract representation of the real world thing. So even though you have all this data, you're going to pick and choose what data is relevant to the specific simulation you're performing, which really depends on the specific research question you're trying to answer. Once you develop your model, then you validate the model. What is that? Validation. We're going to have two terms in this class, verification and validation. And validation means, what do you think? I mentioned it a couple times. Just talk.
It's like, is this what we want? Basically, like, is what we're in the software.
Spoken like a software engineer. Yeah.
We're validating that what we created is what the stakeholder or the customer, in this case us, wanted.
Okay.
Right? Whereas like verification is making sure that it actually meets the requirements.
Okay. That's a perfect software engineering answer. And it's slightly different in modeling and simulation world.
Exactly what I was going to say.
Okay. So here what validation means in the simulation world, validation means, does it match real world results? So I'm collecting real world data, and then I make a model. And what I can do is run some small test cases with my model, usually by hand. I haven't created my simulation yet, right? I can do this by hand and just do some calculations and say, okay, if this is my input to the model, I know what the real world output is because I've collected the real world data, and my model should have some approximation of that real world result. That's what validation means in the modeling and simulation community. In the software world, the reason they frame it the way they do is because they don't have reality, they have a customer. So in the software world, you'll hear people talk about validation, meaning, are we building what the customer wants? But here our goal is to match real world. So validation exercise is about, are we actually having a meaningful correlation with real world results? Verification, just to follow on to what Alex said, once we've got a model that is good, then verification is that the exercise of, once we build that model, once we have the model, remember, we don't have a simulation yet, we just have a model. Once we have the model, we're going to build a simulation that hopefully matches the model. And what the verification activities are doing are verifying that we have actually built our model correctly inside the simulation. Which actually does have that does align with the software engineering idea of verification. All right, so then select an appropriate experimental design. We've got some lectures on that. Basically, here are my variables, and then you play games with, okay, how many test cases do we need to run? A lot of times what you do is, let's say you pick, there are 3 variables of interest. And so one way to do your experiment design is just to say, here's variable A, B, and C, and I'm going to arbitrarily assign a value of A called high and a value of A called low. And I'm going to run 2 runs, one with A high and one with A low, but B and C are the same. Then I'm going to do the same thing with B, and I'm going to run 2 more runs, one with B high and one with B low, but A and C stay the same. And then I'm going to run, you get the idea, C high, C low, but A and B stay the same. And that's a basic way to do some block experiment design. Now, the full experiment design would be to every combination of high-low, which in this case would be 8 different cases. If you have a lot of variables, you can't do all combinations. But that's a basic way to pull together an experimental design. Once you've got your design, then you establish what your parameters are going to be and perform the simulation runs. If you are very, very clever about creating your simulation, you can actually set up a series of scenarios and hit the go button once, and it'll run scenario 1, spit out some results, run scenario 2, spit out some results, run scenario 3, spit out results, right? That's like the holy grail of this stuff. Otherwise, you have to manually set up the conditions and then hit the go button, and it'll give you specific results for that one scenario. That's a more common way to do it, because not everybody is able to have the time to invest in creating the thing that ultimately saves you time later on down the road. It's like using, if you guys are doing any software testing, it's like using automated software testing tools, right? You'd much rather, if you can, set things up to run automatically. Once you get all your simulation runs, oh, by the way, I'm going to warn you right off the bat. One of the hidden traps here, once you create a simulation, you can get so much data. And you kind of need to have a data plan ahead of time. How am I going to store the data? How am I going to organize it? How am I going to use it? So that when you have all this data, it's not just a big pile of garbage. It's actually something that you can then use and ingest and interpret. Okay, that's kind of a hidden trap. So I'm telling you right up front, we're going to have to, you need to think ahead to, okay, and it can be something as simple and mundane as, how do I name these files? Right? If I just name these files results A, results B, results C, that's probably no good, right? I probably need to have scenario 1, blah, 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 run 1, maybe a date, et cetera, you know, something. It could be something that mundane. In a complex system, you actually build multiple systems. You build a simulator that will spit out results, and then you build a whole nother piece of software that takes in those results and does some kind of analysis and visualization for you. And in a really big system, you have a third system just to build the inputs to the simulator. So for example, some of you guys use, did I say somebody here use Nastran as part of your programming and part of your course? Okay. We know the AE students use Nastran. They also learn early on in EGR 120 how to use, what's that CAD system they use here? CATIA. So guess how they make their Nastran models? They make a CATIA model, and then they can port it over to Nastran, and Nastran has become, it's not smart enough, but capable of importing CATIA models and converting them into finite element models for use in Nastran. Very clever. So CATIA serves as a whole other piece of software whose sole job in that case is just to create the input for the Nastran. Okay, so now you've performed your simulation runs, you've saved all your data, and now interpret and present results. And again, this is why you need to have a data plan ahead of time, interpret and present results. If you ever had participated in trying to get a grant from the National Science Foundation, one of the things they often ask for in your proposal is, hey, what's your data plan? You've experienced this, yeah. Okay, and then once you have the results, then you can say, here's what we should do. Here's how you get the squirrels out of Garfield's yard. Stop feeding them. I feed them. That's my problem. Okay, so that's the run through. If you look at this, it's the same concept. I won't walk through it twice. The same thing. They focus on things a little bit differently. They name things slightly differently, but basically same steps. Those papers are in Canvas. I don't do any enforcement mechanism for the papers that I'm asking you to read, but if you look in the module, it says here's your required reading, here's some optional reading. And so my expectation is that you are reading the required reading. If reading conference papers is a new thing to you, you may find it troubling at first to get used to the kind of language and style that they write with, but that'll pass pretty quickly. It's an excellent skill to get. If you are in a grad program, you absolutely should already be competent at reading conference and journal papers. And the rule of thumb used to be a grad student should read at least one paper a week. And that by reading, I mean, it's a 4 to 8 hour exercise to read the paper kind of thing. You're really ingesting it. So I'm getting you. Oh yeah. I'm often the same way. I like to put on some ambient music that won't distract me. But once you get used to the writing style, then it helps. And by the way, getting used to that writing style by reading it is also an excellent way to learn how to write it. And if you look at how I framed the project report that I want you to write, it pretty much follows the standardized steps for how to write a conference paper. Okay. Now what? Let's do some kind of interaction to break things up before we jump into all these definitions. What have I concerned you with today? What have I frightened you with today? Oh, you'll get over that fear. If you are, oh, my brain. Oh my gosh. Yeah.
What happens if you reject those?
Then we do another one. Usually the way that'll work, first of all, part of what I want to do today is get some informal understanding of what you think you might do. And so we can massage that now. And then if it's rejected, usually it's not like this whole topic is yes, it's usually let's modify it. Almost always. And I'm going on my experience with CS225, where I did lots of projects, and CS350 the last couple of semesters, which is a team project. I was really proud of my teams this last semester. They all but one of them did quite well. Yeah. Oh, and by the way, it's kind of difficult now because a lot of faculty are gone for the summer. But if you're working with a faculty member and they need a simulation, by all means, let's get a customer and build something hopefully that they can actually use. One of the things I hate is for students to do a whole lot of work and sweat and strain throughout a whole semester and build some kind of a software product. And then once class is over, they never see it again. And I'd much rather you build something that you think you're going to use after this semester, or if you can find a customer that person can use. So in SC300, which is a software engineering course with teams doing projects, we had 9 teams and 7 of them had customers. And of the customer, all of them were like on campus. And of the customers, I think 4 of the teams actually delivered a product to the professor that they can now use in their classes or wherever. One was to be used up in the telescope room. One was for human factors to do some testing, online testing. So if we can pull that off, that's great. Other questions? Okay. So let's run through these, and then we will and then we'll pause, and I want to talk about, get your project ideas from, and have you guys talk to each other about your project ideas too. Okay, this vocabulary is very specific jargon to the modeling and simulation community. You know, every community has their own jargon. And most of this stuff is well defined. This term I mentioned the other day, fidelity, is not well defined. Resolution, kind of defined. But some of these are pretty well defined. And when you read modeling and simulation conference papers or journals, you'll find this kind of language or textbooks. That's where I got them from. So feature, a measurable aspect of a real world system. So remember what we said, a model is an abstraction of a real world system. And so what you're doing when you're building a model is you're actually picking and choosing what features from the real world are important to you. And it has to be measurable. Why? So that you can model it. Referent is an idea that the modeling and simulation community uses that nobody else ever hears of. So it turns out you don't model the real world. And we can get into this big philosophical argument about why that's impossible. You model something called the referent. And the referent is an idealized representation of the real world thing. So for example, if I wanted to model this thing in a virtual space, you could say I'm going to model the table, but what I really have to do is say, oh, this table has a certain height and width and length, and I would measure those things. That becomes my referent, right? It's like so close to the real world, but it's not really the real world because it's how you measured the real world. Now, philosophically, is that the table or not? Okay, so if I said, oh, I've got a table and it's, I don't know, what is this, 48 by 24 by 33 high. Am I talking about the table or is that the referent? It's really the referent. So there is a distinction that you can make and sometimes need to make between the real thing and what you think the real thing is. And again, this gets into a whole, is reality subjective or objective, and Plato's world of ideals and blah, 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 right? So you can get into a long thing there. But this notion of a referent, that's a term that I never heard outside of the modeling and simulation community. But that's what your model will be based on. And that's why the feature has to be a measurable aspect of the real world so you can create your reference. Then an attribute is that representation of the feature in the model. So we've got in the real world a feature, and then in the model, we're going to call that an attribute. And the attribute is the model or form, right, the mathematical version of the real world feature. And the reason it's good to keep these things clear, it's kind of pedantic, but it's kind of useful because you often find that you're going to need to distinguish when you're talking about these things about, wait, are you talking about the real world or are you talking about your model or are you talking about your simulation? So you always need to know where you are and what you're talking about. Once you have the attribute, then these attributes, remember, once you execute a simulation, the simulation is going to have changes in state over time. What does that mean? It means the values that you've assigned to at least one attribute changes over time. How does it change? You have some kind of an update function attached to that attribute. So for example, you've got an agent walking around in flat world, and all it's got is an XY coordinate, right? And it's walking north, so its Y location keeps changing. Okay, how do you make that agent move around? First of all, the feature is where is it in the real world? The attribute is what's its X and Y coordinates. The update function is how do I modify the X and Y coordinates? By the way, a bunch of these things, right? Fidelity, like I said the other day, the idea is how well is it representing things? In a finite element model, if I'm doing this desk, am I doing it with 2 elements that are 2 by 2, 2 feet by 2 feet, or am I doing it with I don't know, a million elements that are, I don't know what the thing would be, a 1/4 inch by 1/4 inch? People talk about that as the fidelity. To what degree are you simulating things and to what level of granularity? Now, as I mentioned yesterday, though, there's really there's no measurable metric for fidelity. So that it's very difficult to compare fidelity of model A to model B because the modeling simulation community really has never agreed on a formal definition of that. Resolution is similar to that, scale of the model. And then we can talk about state. The state of a model. If you take all the attributes and all of their values, and you take a snapshot, that's the state. Now, once you modify that model and you get a state change, that means at least one attribute value has changed its value. So you can think of models as moving from state to state to state to state. And you computer science people, I hope will appreciate the idea of a finite state machine. Basically, what we're talking about here is a state machine approach. You can approach your models that way. Even though they may be, we like to think of them as continuously changing, they are not in the computer world. If you think of a merry-go-round, right? Continuously changing. Now, how are you going to model that? You're going to model that with an update function, and that update function says, okay, every time I update this, this represents 1/2 second of real-world time. In other words, what have you just done? You've taken continuous time and chopped it up into 1/2 second increments, and now you've got state, 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 state. Right. These are minor distinctions that tend to make a big difference if you're not aware of it. You fall into some bad traps about what it is your model is telling you, how are you going to define your model, and the real big ones, how are you defining your model, how are you defining your software? Those kinds of questions you need to be aware of these things so you can ask yourself the right questions to get your models developed. Completeness. A model or a collection of models that contain everything they need to have update functions addressed for all of their attributes. In other words, it's a complete simulation. So for example, if I said, I've got a model of a car. Now I want to run a simulation. The problem is the simulation is not complete because the car needs to have an environment to work with, right? So there's no way to have a good update function, right? You don't have a good update function for the car. You could have an incomplete model. You might have attributes that don't have update functions. Why might that be? Any thoughts? I can't think of, I can think of why. I can't think of an obvious example. Maybe we could.
A reason why you would have an update function?
Yeah, maybe you have an attribute, but you don't have an update function for it. In other words, your model's incomplete. Is there a legitimate reason for that?
Blinded for a sensor.
Pardon?
You want to simulate a malfunction.
Okay, you could simulate a malfunction. Or what if the update function isn't dependent upon the models, that particular model's agency, but something else drives it? So something else may have to have the update function. Right. Then, once you put those two models together, then you would have completeness. Ambiguity, if you have more than one update function for a single attribute, that would never happen. It probably won't happen in this class, but you can imagine if you start to have very large, very complex systems. The software engineering community worries about this kind of thing a lot. They worry about having competing requirements that contradict each other. That would never happen, right? Yeah, it turns out if you have very large systems with hundreds of requirements, you can develop these things. If you have very large models, and portions of the models are developed by different industries, different groups of people, you can develop these kinds of issues. So again, I doubt we're going to have ambiguity in this class. Just be aware that it exists. Verification and validation we've talked about, right? Validation in the modeling and simulation world means comparing against real world results. Verification means once you define what your model is, did you incorporate it correctly in the simulation? That's what verification is about. And that's different from accreditation. Accreditation means there's some external body, governing body, that gets to look at your work and say, I approve it, and puts the stamp of accreditation on. Within modeling and simulation community, there's something called the high-level architecture that we'll talk about later. And there are groups of people like the CISO standards, international standards organizations, that could come and look at your model and say, yep, that really is an HLA model. It really is a high level of architecture model. You met the formatting for that. Now these guys are going to be, on your first homework, I've got some questions about this. I'm giving you, I say, hey, is this an example of composability or is this an example of interoperability? And the idea here is, for composition, it is common to take two models and put them together to form a larger model. Okay? And my example here, I think I said is somewhere down here, I've got an example. It is common, or it has been done in the DoD world, to model a single tank that has a hull and a turret as two models. One is the hull and one is the turret. And then you put those two models together and now you've got one model called tank. But it's really two models composed together. In order to have the composability work, you have to have two things playing together. One is this notion of syntactic composability. Now, by syntactic composability, we mean that the two models will share and exchange the same data information. So it's basically about data types. And semantic composability has the meaning of things agree between the two models. So, for example, I might have model A and model B. I want to compose them together to create larger model C. And they're going to pass time information back and forth. So they're going to, basically, I'm going to represent time as a float variable, right? So they're passing a float back and forth. That's syntactically composable. One of them is sending a float. One of them is expecting a float. So that's syntactic composability. But it turns out that one of them, when it sends a value, is sending that value in minutes. And the other one, when it's receiving the value, is receiving the value as seconds. You can see where that would be a problem. That's semantic composability, the meaning of the number that was sent, as opposed to the format of the number. So syntactics, remember, syntax is always about what is a legal construction of a string, like in syntax and in natural languages, what is a legal construction of a sentence, right? Whereas the semantics is what is the meaning of the sentence. We've had some high-level failures, high-profile failures occur, sometimes because of syntactic, sometimes because of semantic issues. Years ago, it's been a long time now, we lost a Mars mission. We lost it because of semantic problems. One entity was transmitting in metric units. One entity was interpreting in imperial units, right? And instead of going into orbit around Mars, I think it shot off into space. Or it crashed. Either way, it didn't do what it was supposed to do. Right? Yeah. So these are these are things that show up in the modeling and simulation world. And the reason it shows up a lot is because once you are doing sophisticated models, it is very common to build them in piece parts and compose them together. Like I said, a standard model for a tank, at least through a piece of software that the DoD was using widely 20 years ago, was to have a hull and a turret and put them together. And what's interesting, maybe it's interesting, there's a story about that. When they first created this software, it was all tanks, it was all vehicles. And then the DoD said, hey, this is really cool. We want to have people too. And so we want to represent individual soldiers. And so they said, okay, cool, we'll do that. And so how did they represent a soldier? As a hull and a turret. They already had the tank model. They just said, okay, this is the soldier's body and this is the soldier's head. So I know where he's looking and I know where he is and how he's facing with the body. But the upshot of that was when they first were testing it, the soldiers couldn't go through doorways because they were as big as a tank. They forgot to adjust the parameters. So that's composition. Now, this is a closely related topic is interoperability. And the only real difference here, and my gosh, you can make an argument each way. If you want to be a jerk, and who doesn't? Someone could come up to you and say, well, I'm composing these models, and then you could convince them that they're actually doing interoperability. And once they agreed with you, you can convince them that they're actually doing composability. That's how closely related these two things are. There's almost an arbitrary distinction. And the idea with interoperability is you still need to do the composability stuff, but the models remain separate. So for example, a classic composition example is the hull and the turret compose one model called tank. Now, what if I put two tanks in the same simulation? That's interoperability because they're maintaining their distinction as separate entities. That makes sense? So when I have my opera problem is a bunch of robots in a room trying to get out. So in my simulation, I have a simulated robot, a simulated robot, a simulated robot. They have to be interoperable with each other. So for example, maybe each of us built our own model of a robot, and we wanted to put all our models in the same simulation to do the opera problem. All of our models would have to be interoperable. Why? Not composable, interoperable. They're not composable because we're not creating a single larger thing. They're maintaining their individuality within the simulation. By the way, how would we accomplish that?
Set parameters ahead of time.
Yeah, we would spend several months ahead of time arguing about what needs to be in and out of the model, and then we would spend 3 days making it. There is a community of software people that believe in something called component-based software. And component-based software means I have a bunch of software, pre-built components, and I never have to write software again because all I have to do is go to the library of components and take this one and take this one and take this one and stitch them together, and I have a software product. And that has never been a successful paradigm. But the modeling and simulation community has a similar idea. They, 20 years ago, were trying to build up libraries of models. And you could basically check out models, and if they were composable and interoperable, then you could use those instead of having to start from scratch. You could use those to build up your simulation. It turned out to be a very difficult problem, and the funding for it pretty much dried up, and so they never did achieve that. But that's still something that's out there. It is, again, common if you are building large software systems of any type, including simulations, to have multiple corporations involved, and then they have to work together to try to put all their stuff, all their components together into one larger system. Okay, so these are very specific, these terms, very specific to the modeling and simulation community. And, you know, when you're in an interview, if you're going to be hired by someone to do some simulation, you know, try to review this page and purposely bring those terms up in your interview. We don't talk about, we talk a lot in the software community about, okay, I have in the systems community, because that's what systems is all about, is look, I have a complex system and we know this component is built by this corporation, this one's built by another one, this one's built by another. How do we make the system come together and play? It's a common topic. They don't use these terms necessarily, right? These are the software engineering, the modeling and simulation community's terms for these things. Okay, I'm not going to walk through this wall of text. There is a, on Canvas, Michael Petty, who I worked with at UCF for a while, wrote a pretty good paper about composability that he and I argued about for the next couple of years. But it goes through these topics, and I've already discussed these topics on the definition page. But that's not a bad paper to read. I think he was optimistic about the degree to which these things could be achieved. Okay, yeah. So be aware, read through this stuff, and read through the papers. By the way, you'll notice that all these notes are listed as CS350, and the papers are CS350, paper 1, P1, P2, P3, paper 1, paper 2, paper 3, that kind of thing. You know, that's where I developed all these notes a while ago. So I think they're a good set of notes. That's why I didn't change them, and they do apply to the CS528 course too. Since we're going to focus on agent-based stuff. Okay. Per the schedule, we're supposed to get through these things today, and we have. So I'd like to spend time discussing your project topics, and I'm happy to work one-on-one. We can start out sharing as a group, but I'm happy to go one-on-one with you. And as I'm doing that, you guys should talk to each other about, hey, what do you think about this? What do you think about that? Sir.
So I was just playing with the idea that you're doing a little research. I would like to look at taking what was my senior design project, which was a hexacopter drone that can transition to forward flight, and first figure out how to get it into ROS itself, the robot operating system, and learn how to program aerodynamics into that, which it's capable of doing. And then from there, I would then like to start teaching it how to operate with other robots using the GPS interconnection between the Wi-Fi system that it has.
Okay. So here's the good news with simulation is you can start out stupid simple. You can start out with this thing is a point with mass, but no physical moments of inertia or anything like that, right? So then you don't have to worry about rotations or the actual physical way it flies. And then of course, classic physics, you're in a vacuum, right? So we've got a circular dot in a vacuum, and then the interactions are, what was your interaction via through a
Robot operating.
No. It was you mentioned like interacting with other robots via.
Basically another the same model hexacopter.
But is it through a radio link or a
Wi-Fi?
So yeah, so if you could do a really high fidelity simulation, you're going to do what RS-232 communicate or whatever the proper communication protocols are, or you could just magically say, I received the message. So you can start out with stupid simple and then work your way towards, towards more and more complex. Then the question is, what's the goal of your simulation? Because that's going to tell you where you need to spend your effort.
So I have two goals from what I'm personally saying. One, to give back to the robotics program to be able to have the ability to simulate drones because they don't have that. Right.
Good.
And give them that because there's open source stuff, but it's not compatible with the stuff we use at school. So I want to give them that. That was one limitation factor for my senior design project was we couldn't simulate our project quickly enough because we had so many other things happen.
Right.
Yes, it's on a simulation product like that. The other thing is I did want to start doing experimenting with the information sharing between the two robots, which is not something that is taught in the in school. So this is a
Okay.
robot operating system because that's something they want to add, but they don't know about.
Yeah. Okay, yeah, so that's a good, I like the information sharing aspect too, and you may only focus on one or the other. You know, you may keep your physics to a minimum and focus on how the behavioral changes occur, or you may choose to expand the physics if that's more useful to the robotics community here on campus. I noticed, by the way, you mentioned an interoperability problem, right? There are tools out there, but they don't interoperate with what we have. So it's a real problem. Yeah, those are positive things, and we'll have to frame it as a like a research hypothesis. But then you're already tied into that community, the robotics club on campus. So you want to talk to them. I would say treat them as a customer.
I'm gonna go talk to Dr. Garcia right
Good.
now.
Okay. Yeah. Treat him as a customer. Him or her. Treat her as a customer and say, you know, what would you like to see that would be a useful simulation tool for you guys to move forward, and then that'll help shape the rest of your discussion. Yeah, that's very, very, very appropriate. Who else? I don't know. You gotta have, but I don't know, but right. So let's do that part of the sentence.
I have two different ideas that I'm split between. First was like two teams or tribes of agents where there's like a pile of food in the middle and both sides go to get the food. There's a limited amount, but it replenishes over time.
Right.
And then like you could tweak for the teams how much they want to share between their teams and if they even want to share with the other group. And the other one was the fuzzy cognitive map that you were saying.
Right.
And implementing I guess agents like you were saying somewhere.
Okay, so yeah, so the fuzzy cognitive map, and I can, if you send me an email, I'll send you some papers on it. Fuzzy cognitive map, I would like, because I want that as a tool. And basically what I want is not a specific fuzzy cognitive map of, oh, look, here's what the spice trade looked like in 1600. I want one that is, you could create the spice trade in 1600, but you could also create any other system that you like. So that's my personal goal. It would be, yeah, if I could get a FCM tool on it, it'd be great. The one with the altruism game, the resource, then you can play around with, okay, yeah, we might have it where there's a food source in the middle, but now you have a lot of rules about is there conflict, blah, blah, blah. You may also have that the food sources are spread out among flat world and generate and play, then you can play games with what if there's an area that's basically desert? What if there's an area that's very lush? How does that affect the movement of the different agents? There are those kinds of games too. So be aware that those are out there. They're both acceptable products. If you do the altruism game version, you would need to come up with, again, give me a specific hypothesis. And a typical one for that is, what's the ideal level of sharing? Is there an ideal level of sharing? I had a student publish a paper 15 years ago doing exactly that. He created the altruism game, and then he played around with the resource rates and the altruism, the level of sharing, and found that when there's a lot of resource, doesn't matter. There's no good, every policy wins, right? When there's virtually no resource, being non-altruistic is actually helpful. And then there was a sweet spot where being like 60% altruistic was helpful. So come up with your research questions. Both of those are acceptable. No?
I have an idea.
Good, there you go. Sam's embarrassed to say it. We're all friends, right?
I don't know how I'm gonna go about it, but the idea is smart traffic interaction.
Okay.
It would be a model on how motorcycles would interact with autonomous vehicles and human-driven cars in mixed traffic conditions.
Oh, okay. That's good. Now, the hard part there, and oh, by the way, so here's the good news and bad news. The bad news is if you're creating from scratch, I've always had issues with what's a good way to create actually the roadway. That's a tough one. I mean, you'd think it'd be stupid simple and it's not. But here's the good news. I think I would be almost certain that you can download a free traffic simulator. And that's the good news. So all that environment is already created for you. And a lot of the work is done for you. The bad news is often if they're packages that you already exist, you can't break into them to create your own unique behaviors. So you'll have to do some research and see. And the reason I know that you can get traffic simulators is I judged a high school science fair last year, and some kid had a traffic simulation, and he was using some kind of, I forget what software he found online or his dad found online or something. Yeah.
Well, that'd be a good
But
start.
and even if you can't use it, you may be able to get a good idea by reading about whoever did those freely available traffic simulations have published somewhere, and they're going to tell you how they did it. So and that way you can recreate what they did. Yeah, you think it'd be simple, but then you start to say, okay, I've got an intersection, and the intersection has 2 lanes northbound, 2 lanes southbound, and turn lane. And then 1 lane east-west and turn lane. Right away, that's a difficult thing to model and do well. I've not had, I don't think I've had any students that I've been happy with, but it's a good challenge. And it is doable once you figure that out. What else we got?
I was gonna do a fuzzy copy.
Okay.
I don't know, like, I liked when you talked about it, and you have a specific.
And again, you don't have to have a specific, if you're creating the tool, right, which is my selfish personal goal, is to get a tool, then you use some kind of a scenario as a way to demonstrate that the tool works, right? To convince yourself that the tool works. And that becomes almost secondary. But yeah, you can come up with any kind of a research question. And again, if you email me, what I'll do, since a couple people are interested in it, is I'll post those papers on the Canvas site for you. But I'll need an email to remind you.
I really don't.
No
know
idea.
yet. I have a lot of reading to do.
Okay. Any notional thought?
I don't know if I could relate this to the topic, but I know in general I'm very interested in like where software meets human language and linguistics. I don't know if I could do anything with that.
How so?
Just, I don't know.
Well, forget the simulation. What's the question in your head? You said you're interested in how software meets with human language. I don't know what that means. So explain to me what the interest is.
I guess I'm mostly thinking of like large language models and whatever they do at places like Google Translate or Verso, but I'm very embarrassed right now.
Okay, I don't want to embarrass you then. All right, so you've got the germs, you got the beginnings of a good topic there. And like I mentioned, last year someone did a how do I make good prompts? Kind of yeah.
Gonna do the advanced air mobility work, because that's what I'm also currently doing research on.
Right.
And I'm gonna need a simulation for that.
Okay, so there you go.
Yeah,
Is that for a grant or for your PhD or for what? Okay, and I'm sure Omar will give you lots of good advice as to how to go through with that. Yeah. Okay.
If you don't mind, I do have a suggestion that just occurred to me. Why not, if you don't mind?
Yeah.
What about looking at how, language models handle a new and unknown language without syntax?
Ooh.
I'm gonna type that in my,
Because if you want that, I know that I'm big into the game Star Citizen. There is alien racism there could be, they literally have had linguistic compressors generate an entirely different language base. And it has auditory, like written language and everything else. And you could feed it into it with no equal sign and put it in sentence structures and see what it comes out.
okay.
And then you could figure it out yourself by figuring out what it's going to say.
Thank you. I have that noted down.
But that'd be useful for whenever the aliens finally decide that we're no longer savage barbarians.